Okay, so we're going to pick up in the lecture notes from where we left off, which was subtracting whole numbers. I have some instructions for how to subtract whole numbers here. You can read those on your own, but let's use the algorithm that should be familiar for us by now. Okay, let's do this problem. A car costs this much, $14,497, and you have a down payment of $3,824. Find the exact amount needed for a loan by finding the difference between the price of the car and your down payment. Check your answer by adding. So, difference means subtract. These are the two numbers we will subtract. We subtract them by writing 1 on the top. This is called for the vocab we learned in class, the minuend is the number that goes on top, and the subtrahend is the number that goes on the bottom. So the minuend is the number that you are starting from. This is the starting cost of the car. You have paid this much as your down payment, so that's how much of the cost you no longer have to pay because you have already paid it. And when we subtract these, we'll find out how much there is left to pay. So 7 minus 4 is 3. 9 minus 2 is 7. 4 is smaller than 8. So I'm going to have to borrow. I take 10 from the next column over. 14 minus 8 is 6. 3 minus 3 is 0. And 1 minus nothing is 1. So the amount that is left to pay is 10,673. This is called the difference. So minuend minus subtrahend is the difference. Not that you need to know these vocabulary words, it's just kind of interesting that they exist. Let's do a couple of these together. And this one I'll let you do on your own because it's going to practice two skills. One is word problems, like decoding English words and turning them into symbols and numbers. And two, it'll also help you practice going from English names of words to Arabic numerals, which was part of the earlier section. So I'll let you do that one on your own. But, we forgot to check this. We can check through addition. The way you check through addition is you take your answer, so the difference, plus the subtrahend, which is that number. We have to check. So 3 plus 4 is 7. 7 plus 2 is 9. 6 plus 8 is 14. We carry the 1. 1 plus 3 is 4. And 1 plus nothing is 1. This is, if we did both the addition and the subtraction right, this number should be the minuend, and in fact it is 14,497. We either did both of these right or we did both of them wrong in ways where the two different errors cancel. So, because it's unlikely that we did two different things wrong in ways that are exactly opposite from each other, we can feel pretty comfortable that we did it right. Although, that said, I do see that on tests where people make two complementary wrong answers that cancel each other out. So, I guess we still have to practice so that we can do it correctly. Let's do these ones together. So I subtract by taking the first number and putting it on top. 702,758 minus 345,119. There we go. Can't take 9 from 8, so I have to borrow. 18 minus 9 is 9. 4 minus 1 is 3. 7 minus 1 is 6. Can't take 5 from 2. And I don't have a 10 to borrow from here, so I'm going to have to borrow 10 from the 70. This becomes 69. 12 minus 5 is 7. 9 minus 4 is 5. 6 minus 3 is 3. So my answer is 357,693. And then let's do this one here. So again, I write the first number on top and the second number on the bottom. 7 minus 3 is 4. 3 minus 2 is 1. 8 minus 2 is 6. 3 minus 1 is 2. And 1 minus nothing is 1. My answer is here. I'll let you do this one and, again, F on your own. I think I'll let you do the rest of those on your own. Let's move on to the next objective. So we're going to estimate differences by rounding. Oh, was I supposed to check the answer? Check answer with inverse operation. Okay. Let's check one of these. I'm going to check the longer one. You can check on your own, but we're just going to take the answer and we're going to add the subtrahend and see if we get back our top number, the minuend. 9 plus 9 is 18. We have to carry a 1. 1 plus 3 is 4. 4 plus 1 is 5. 6 plus 1 is 7. 7 plus 5 is 12. We carry a 1. 1 plus 5 is 6. 6 plus 4 is 10. We carry a 1. 1 plus 3 is 4. 4 plus 3 is 6. And we get a match. Oh, wait. 1 plus 3 is 4. 4 plus 3 is 7. And now we get a match. There we go. This is the original number. So we have correctly done that. And now we'll move on to here. We're going to estimate differences by rounding. So we're going to do this using front-end rounding and then rounding to thousands, hundreds, and tens. So front-end rounding, we want to round to the first number in each of our numbers, the first digit in each of our numbers, I should say. So I want to round to this 10,000. That means I look at the thousands to check. 4 is less than 5. 0 through 4 round down. So this will round down to 10,000. This number here, this is the digit I'm rounding to. I'm rounding to the thousands place, so I'm going to check my hundreds. 8 round up, so this 3 turns into a 4. And then all of the other numbers turn into zeros. I now have 10,000 minus 4,000, which is 6,000. So that's my estimate using front-end rounding. Round to the thousands place. So now, let's clear all of this away. Do it again. So now I'm rounding to the thousands place. So I'm rounding to this position and this position. Notice this is the same place we were rounding that number before, so it's going to end up being the same as before. But now, since we're rounding to this 4, we have to check the hundreds position. 4 is rounded down, so this rounds down to 14,000. 14,000 minus 4,000 is 10,000. And again, round to the hundreds place, we're rounding to this position and this position. We check here, 2's round down, this is 3,800. 9's round up, so this is 14,500. 14,500 minus 38,000. At this point, it might be appropriate, like you might want to start writing it vertically and using the algorithm. So I'm going to do it like that. Zeros subtract to give me 0. Can't take 8 from 5, so I have to borrow. 15 minus 8 is 7. 3 minus 3 is 0. 1 minus nothing is 1. So this gives me 10,700. And then we want to round to the tens place. So now when I round, I'm rounding to this position and this position. I check this digit and this digit. 7 rounds up. That means that 9 turns into a 10. That means I have to carry. This goes to 14,500 again. 4's round down, so that 4 turns into a 0. Everything to the left of it stays the same. At 14,500, again, we might want to do this one vertically. 14,500 minus 3,820. 0 minus 0 is 0. Can't take 2 from 0, so I have to borrow. 10 minus 2 is 8. Can't take 8 from 4, I have to borrow. 14 minus 8 is 6. 3 minus 3 is 0. 1 minus nothing is 1. The answer is 10,680. And it says, which place value or method of rounding do you think is best for estimating the difference? That actually, it really depends on what you're trying to do. The smaller the places that you're rounding to, the more accurate your estimation will be, but also the less time you save. The reason you do estimations, there are two big reasons to do estimations. One is because the problem is complicated and you want to save time. You don't need an exact answer, you just need something that's close enough. That's one reason you might estimate. The other reason you might estimate is you're trying to check that an answer was done correctly by saying, is my actual answer close to the estimated answer? The estimate is, in this case, we're not looking for something that's faster, but we're looking for something that's easier. We say we do an estimate because it's easy to calculate. We feel pretty good that we're not making mistakes. So we do the problem, we do an estimate of the problem. We say if the answer we get is close to the estimate, we think we must be in the right ballpark. We have reason to believe that our answer might be correct. So those two goals in rounding, you're either trying to do it faster or you're trying to do it easier so that you can compare your answer to an estimate. Like, what does it mean by what method of rounding is best? Is like, if you round it to too big of a position, your estimate is going to be further off. On the other hand, if you round to too small of a position, you're not saving yourself any work. You might as well just do the problem again. So it's kind of tough. Often, if the purpose is just to check an answer or just to get a ballpark estimate, front-end rounding is fine. So, but it's kind of up to you. Okay, so now we're going to do more problems like what we did. We have to make sure to round to the right spot. So this is rounding to the nearest 10,000. 10,000 is here. There we go. 10,000 is here, so our check digit is the thousands place. 10,000 is here, so our check digit is the thousands place. Ones and twos round down, so this will round to 330,000, and this one will round to 190,000, and we can subtract that. If we want to, we can write this vertically. Can't take 9 from 3, so I borrow. 13 minus 9 is 4. 2 minus 1 is 1. Our estimate is 140,000. I'll do this one next. So let's practice converting this from words to Arabic numerals. So we're doing a difference, so we are subtracting. I'm going to write this vertical. We also want to use front-end rounding. So, yeah, I'll write this vertically. We have 19,607 and 3. Wait. 607. 607. There we go. The next number is 333. And we are subtracting those. So front-end rounding means I'm rounding to this position, so that means this is my check digit. 9's round up. So this 1 turns into a 2, and all of the other digits turn to zeros. I have 20,000. Here is where I'm rounding to the front end, meaning the first digit. This is my check digit, that rounds down, so I get 3 with 2 zeros. And then I subtract. I can't take 3 from 0, so I have to borrow from the 20. 20 turns to 19. 10 minus 3 is 7, and then 19 minus nothing is 19. There is my answer, 19,700. Okay, next objective. We're going to use inverse operations to check an answer to either addition or subtraction. So basically what we've been doing, but the subtraction from this video and the addition from class. So Hassan needs to take 9 apples to school. That is a large number of apples to need to go to school. He has 4 already. Brenda wrote this as 4 plus 9. Sorry, 4 plus 5 equals 9. Joe wrote this as 9 minus 5 equals 4. Who is correct? They're the same, right? These are the same statement. So he has 4. He wants to get to 9. He has to fill in the blank. Filled in the blank with a 5. That's great. Same thing here. We have 9. Oh, this is an interesting way of writing it. That's kind of funny. So with this one, 9 minus something equals the 4 apples that Hassan already has, and we still fill in the blank. I would say the most direct way of doing this would be, I want 9, I have 4, I subtract that and get 5. Like, this is more reasonable, I think. I know this information, I know this information, this is the thing I'm trying to find. But doesn't matter, it's the same statement either way. Inverse operations. How can we check whether this minus this equals this using an inverse operation? Well, since the operation is subtraction, the inverse operation is addition. We're going to try adding these two numbers together and see if we get this one. So 530 plus 418. 8 plus 0 is 8. 3 plus 1 is 4. 5 plus 4 is 9. And that is a match. So yes, we now have checked. How can we check? We check with addition. And that's how it looks when you check it. How can you check this? Using an inverse operation. Well, we're going to subtract. What we're going to do is, since the operation is addition, we will check by subtracting. This number goes on top. Either one of these goes on the bottom. It doesn't matter. I'll choose this one just because it's smaller. And then we subtract and we find out if they match. If the answer of this problem matches with the other number. So, can't take 8 from 6, I have to borrow. 16 minus 6, 16 minus 8 is 8. 5 minus 1 is 4. 13 minus 4 is 9. 48 is a match. So, yes, this is correct. So, says, how do we check this? We check this with subtraction. Subtraction is the opposite of addition. We check by using the opposite operation. Write an equation that contains an inverse operation that could be used to check each given equation. So we use the inverse, so that's addition. We invert, we take these two numbers and see if they add to get this one. 3, 7, 5, 4. And if we do it right, like if this is a correct statement, then we check, we get 7 plus 4 is 1, carry a 1, 1 plus 3 is 4, 4 plus 5 is 9, and yes, this is a true statement. It doesn't actually say that we have to check, it says, how could we check? So this addition means that we're going to check with subtraction. We're going to take the sum, and we're going to subtract one of these two numbers. Let's pick 130 this time. I took the small number last time. I'll take the big number this time. And we check to see, does that equal 62? And it in fact does. So this is a true statement. We go through the rest of them. Okay, module 1.4. We are going to apply what we learned about adding and subtracting to other problems. So this application is if there are two skills that are the most important two skills in the class, one is being able to do word problems, being able to take instructions that are not written in equations and turn them into equations so that you can solve a problem. After you solve, you look at the answer and you turn it back into words to say what the solution means. So there's the going back and forth between we're going to use English. Certainly, if someone were using another language, that would be totally useful. But being able to go between the English words of a problem and the mathematical symbols of a problem, that's probably the most important skill in this class, is being able to convert between the two. And the next one is being able to apply the math that we learn to problems that we encounter in the world. Being able to say, okay, well, what math do I need to use to solve this problem? Real world is, I think, not the best way to describe what we're saying, but I think that that's the common way to word it. So we have a problem here. We're going to use our 4 polya steps, which are to understand, to plan, to do, and to reflect. We want to figure out what we're trying to solve, like what is the type of answer we're looking for, what's the goal, and then figure out what information do we know, what information do we need, and And how do we find the information that we need? What methods are we going to use to find that information? Planning is putting all the pieces together and saying, if I do this, I will get a solution. Doing is all of the calculations that come from the plan. And then reflecting is two things. One is figuring out, does the answer make sense, or did we do something wrong that we need to go back and fix? The other thing is, did I learn anything from this process that can help me solve problems better in the future? So here is our Polya problem solving procedure, our Polya problem solving steps. We're going to apply these to this problem. Okay. Quilt blocks. Fabian is playing around with ideas for putting a border around some quilting squares. He makes the following patterns with different colored blocks of squares. On the border on each block consists of small dark gray squares. If he continues the pattern, how many small dark gray squares will be around the border on the next two quilt blocks? Describe the pattern of change. So, to understand, we want to figure out so when we're doing these math problems, the things we're looking for are questions and commands. So we have a question mark here. That's something we have to answer. And we have a command. That's something we have to do. So if he continues the pattern, how many small dark gray squares? Like, we have to figure out how many of these squares there are around the border on the next two quilt blocks. So we have a first block, a second block, a third block. We need to figure out how many small dark gray squares are on block 4 and block 5. Okay, that's what the question asks. And then it says, describe the pattern of change. So when we figure out the pattern, we can figure out how many blocks, like the numbers for 4 and 5. We also need to write out what that pattern is. Okay, so now we understand what we're trying to do. We have to figure out a number of blocks for 4, a number of blocks for 5, and we have to figure out how to describe the pattern. And we have to figure out the pattern first because there's no way for us to find how many are in 4 and in 5 without figuring out what the pattern is to get to 4 and 5. So we have to make a plan. Well, we may not have enough information for a plan right now. Maybe we have to go back to understanding and figure out. It might be useful for us to count how many blocks there are in the first 3, and then try and figure out if there are any patterns that we see in these first 3 blocks. So first off, we have 8 small blocks here. We have 12 blocks here. So see, I have 4 groups of 3. I have 4 groups of 2 here. I have 4 groups of 3 here. I have 4 groups of 4 blocks here. So I have 8, 12, and 16 blocks so far. So do I see any patterns? I see that it goes up by 4. So I think it goes up by 4. Am I sure that that pattern continues? Well, let's think about, is there a reason why it goes up by 4? Well, it might be because I have 4 sides to the shape, and each side is getting longer by 1 block. So I have this here had 8 blocks. Each side was 3 long. I don't want to count any block twice, so I'm just starting at a corner, and I'm going almost to the other corner. That gives me 2 blocks in the group. And then the next corner gets the next block. That's 2 more in that group. So I have 4 groups of 2 blocks. When I go from this one to this one, I am adding an additional block to each of my groups. So since I'm adding one block to this group and one to this group, and I'm adding 4 blocks because I have 4 groups and each one gets one more block. That's 4 blocks more. If I go to the next one, it's the same thing. I had groups of 3, but now I'm adding a 4th block to my group of 3. I have 4 groups and I add 1 block to each of them. That's adding 4 blocks. I still have 4 groups. I add 1 block to each of them. That adds 4 blocks. I have 4 groups. I add 1 block to each group. That adds 4 blocks. So the pattern is going to continue. I'm always adding 4 blocks at each step. So the description of my pattern is, and I've made a huge mess of all this paper here, but the pattern's description is every time the pattern gets bigger, I add 4 blocks. I think that they call them small dark gray squares. Small dark gray squares. It's good to use the same terminology as the question. So there's our pattern. And then the numbers would be, well, if pattern 3 has 16 and we add 4, then the number in 4 is 20 blocks, and we add 4 again and we get 24 blocks. So we have planned, we did the plan, we reflect to see, does this make sense? Well, we kind of did a little bit of reflection when we walked through why +4 is the right pattern. So we could do a little bit more reflecting we could actually draw out the next step. So this was a 5x5 grid. If we drew out a 6x6 grid, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Now if I count them, I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. It in fact did have 20 blocks like we said the next step would be. We could draw out the next one if we wanted to, but I'll let you do that on your own. So that could be a method of reflection, is trying to solve the problem using a different method. The method we chose here is called the brute force method, meaning we just draw. Like, brute force just means we just do it. We don't look for patterns. We don't try and do things that are clever. We just do it and we muscle our way through whatever difficulties we get. Here's another one, growing dots. If the dots continue to grow in the same pattern, how many dots will be in the next 2 figures? So we want to do our Polya problem solving steps. Come on, erase. So first we try and understand what's going on. Looks like we're just adding a new row of dots to the bottom of this triangle. We also notice that the bottom of the triangle is getting bigger by 1 dot each time. So we have 1 dot on the bottom. Now we have 2 dots on the bottom. Now we have 3 dots on the bottom. Now we have 4 dots on the bottom. So it's going +2, +3, +4. The next ones will be +5 and +6. So we have understood the problem. We want to know how many dots there are. We've noticed a pattern. We make a plan. Plan is we're going to add 5 and we're going to add 6. So let's do that. Well, first we have to figure out how many dots are in this step. Triangle 3 has 6 dots. Triangle 4 has 10 dots. Might as well give our units. If I add 5, like the pattern suggests, I get 15 dots. And if I add 6, I'm going to get 21 dots. So I have made a plan. I did my plan. I have these answers. I want to check to see if they make sense. If I take these 10 dots and go 1, 2, 3, 4, 5, now I count 10, 11, 12, 13, 14, 15. Yeah, I get 15 dots. 1, 2, 3, 4, 5, 6. So 15, 16, 17, 18, 19, 20, 21 dots. I feel pretty good about this. With each of these, again, we're looking for a pattern. So with this one, we are adding 3, and we add 3, and we add 3. So we continue the pattern, and we add 3, and we add 3 again, which is what they gave us because this is a solved problem already. Let's look at another one. Ooh, this looks kind of fun. It's like a rectangle. Let's see. We went this way and we subtracted 5. Still subtract 5. Probably need to subtract 5. So subtracting 5 gives us 108. Going the other way means we add 5. This will be like 103. Is there a pattern going this way? This one we add 29, I think. This one we add 63, and this one we're subtracting 10. Oh, and this is 107. This is 62. And this is subtracting 9. It looks like there are no patterns this way that I see. Just patterns going across. Let's do one of these ones. Plus 9, plus 10, plus 11, plus 12. I'm continuing the pattern. Plus 13 is going to be 107. And the next one will be adding 14, which gives us 121. Okay. Jasmine is playing a video game and currently has 84 points. She needs a total of 243 points to win the game and wants to figure out how many more points she needs. She writes the following equation. This is completely legitimate. If we figure out what goes in this blank, that's the answer that we're looking for. Now, to solve this, though, if we want to undo addition so that we can figure out the missing number, we use the inverse, which is subtraction. I take my total, I subtract my summoned. That's, by the way, when you add, you have a summoned plus another summoned equals a total. Or I think these are also called add-ins. Equals the sum or the total. Anyway, I have 243 minus 84. 13 minus 4 is 9. 13 minus 8 is 5. 1 minus nothing is 1. I had to borrow there both times. So this is how many points Jasmine needs to win the game. Tamales. Lupe made 43 tamales for a party and left them on the counter. Her brothers and his friends came into the kitchen and ate a bunch of them. That's not nice. There's a party, and they ate the tamales before the party. Or maybe they are the party. Are they the party? Or a party? Brother and friends came into the kitchen and ate them. Maybe they are the party. Hmm. You'd say that like they arrived for the party if they ate them legitimately. Otherwise, they just kind of stole her tamales for her party. That's not nice. When she returned, there were only 15 tamales. Yeah, like why would Lupe? Lupe might be nice and make tamales for a party she's not going to, but that doesn't like they should have invited her if that's the case. When she returned, there were only 15 tamales left. Lupe writes the equation in order to determine how many tamales her brother and his friends ate. Why is there a question mark there? There's no question. Lupe writes the equation below in order to determine how many tamales her brother and his friends ate. That should be a period. That's not a question, that's a statement. Explain how this equation represents the situation. Well, this is how many Lupe started with. This is how many they ate. That's how many that's left. Starting value minus the number that's eaten equals remaining value. Yeah. So that's great. We can explain that. You can use your own words to explain it there. Use relational number sense. That just means use the inverse. By thinking about the sides of each part, what operations or inverses might be used? The inverse is subtraction. So there were 43 tamales. There are 15 left. Can't take 5 from 3, so we borrow. 13 minus 5 is 8. 3 minus 1 is 2. They ate 28 of the tamales. Doesn't say how many friends came. That's still a lot of tamales for Lupe to have had stolen from her. Use relational number sense. Okay. Just subtract. I have this number. I want to know something. Plus 51 is that number. We subtract 51 from 143. 3 minus 1 is 2. Can't take 5 from 4, so we take 5 from 14, and we get 9. The answer is 92. Do we have any big numbers here? Okay, let's do this one. This is a little more complicated. So with this h here, we're going to add these two numbers together and get 171 equals something plus 9. Now I'm going to subtract 9 from 171 to find out what goes in the blank there. I can't take 9 from 1, so I borrow. 11 minus 9 is 2, and then 16 minus nothing is 16. That is my answer. So this was a two-step problem. We had to combine the numbers on the left side, and then we had to solve for this blank on the right side. Okay, let's continue. Given the equation, this equation, using words only, come up with as many ways as you can verbally describe what this equation is communicating. So as I said, there are two skills that we really need to focus on here. One is going between words and numbers. What I mean is like, I have this thing written out in numbers and symbols. How do I write that in words? The problems that you do in your real life are rarely going to come in worksheet form. Your boss is going to ask you, hey, how much profit did we make last week? And then you're going to have to say, okay, well, profit means revenue minus costs. I need to figure out revenue. I need to figure out costs. And then I need to do subtraction. So your boss is asking you a subtraction problem, but it's not worded as, hey, take these two numbers and subtract them. It's going to be, hey, I need this thing. You need to figure out what that thing is as a math concept, and then do the math, and then when you get an answer, you need to take that answer and turn it into a business situation and tell me back the business version of that answer. Or if you're a scientist, you're going to have a science question. You're going to turn it into math, you're going to do the math, and then you're going to turn that math back into science. Or whatever it is you're doing. Because if you go back to your boss and say 3, the boss is going to say 3 what? So, anyway, the way that we're going to do this problem is you might say the sum of 14 and, oh, it says using words only. So we might want to write out, do we want to write out the symbol or the words? 14 and 20 is 34, or we might say 14 plus 20 is 34, or we might say, I'm going to be okay with you writing the number. 34 is the total. Oh, I crossed the wrong thing. There we go. Of 14 and 20. Or however you want to do it. But it says come up with as many ways as you could. I'd say 3 or 4 is probably fine. Um, you can translate between verbal phrases and mathematical notation by looking for keywords that indicate addition or subtraction. So things like total, sum, plus, add, words that mean you're going to need to add. Subtraction, you might say difference. You might say, let's see, profit you get by subtracting 2 things. You might say, uh, gosh, what are other words that mean subtraction? We have maybe displacement, distance, things that you'd have to subtract, like how far apart are these numbers? Equals the words is, are, be, um, equivalent. These are all words that mean equal. The same as, stuff like that. So we're going to practice turning words into symbols and vice versa. The sum, meaning our operation is addition, 57 and 68. 57, 68. And then it says simplify, so we add those together to get 125. Subtract 927 from. So this number is being subtracted from, meaning it goes over here. from 1023. We get that. We might want to write this vertically. So 13 minus 7 is 6. 11 minus 2 is 9. 9 minus 9 is 0. There's our answer. What is 342 increased? Oh, increased is a good word. Come on. Why isn't it scrolling? There we go. So increase and grows and decrease and shrinks. Those are all subtracting words and adding words. What is 342 increased by 281? If we want to write this vertically, we can. 3, 2, 6. 623 is our answer. I'll let you do the last one yourself. Application problems using addition of whole numbers. So it says here, we're going to use our polio problem solving strategy and our keywords. These are all words that mean add. We're going to solve these problems like that. If a college has this many freshmen, this many sophomores, this many juniors, this many seniors, how many students attend the college? So from this one, we have to know that all of these words mean students. These are all types of students. And therefore, if we want to know how many students attend, we add up all of the types of students. So I guess this one here, we can't just do this problem without knowing something about what colleges are and what they do. Fortunately, we are going to a college, so we know about these things. So I'm going to add these numbers together. 3, 5, 9, 10, 1, 9, 14, 21, 22, 2, 9, 10, 18, 23, 2, 4, 6, 8. There are 8,320 students. Jason goes on a road trip to Las Vegas from Salt Lake City. He drove 45 miles from Salt Lake City to Provo, where he stopped to pick up a friend. Then he drove 296 from Provo to Mesquite. Is it that far to Mesquite? Provo is at mile marker 260-ish. You have to go across the corner of Arizona, which is about 30-ish miles. Yeah, I guess that's about as far from Provo to Mesquite. Where he had to stop to get gas. Finally, he drove 82 miles from Mesquite to Las Vegas. How far total? We're going to total these things, so we add. Did Jason drive? So we have 45 and 296 and 82, and we add these together. We get 5, 11, 13, 1, 5, 14, 22. 2 plus 2 is 4. Total distance is 423 miles. Okay, now we're going to do the same thing with subtraction. So these are all good subtraction words. We might want to put those on the chart from earlier. By the way, you should look at that chart as you're studying. I was, last semester, I saw more mistakes of misidentifying what operation to do than I'd seen in any other previous semester of teaching this class. I don't know if I didn't stress studying those words enough, or why the students had more problems with that than other classes had, but um, there were lots of times where students were doing problems, and instead of adding, they subtracted, or instead of multiplying, they added. And so I feel like maybe I need to stress this a little bit more. Know these words. Practice making sure that you know what operation goes with what phrase. Anyway, this is the subtraction section. So these will all be subtraction problems, but at a Black Friday sale, you bought $742 in goodies, but then the store gave you a discount of $285. How much was actually charged to your debit account? So here we have 742 is how much you spent. 285 is the money they gave you back with the discount. So if you are spending and then getting money back, you're going to subtract 742 minus 285. Can't take 5 from 2. 12 minus 5 is 7. Can't take 8 from 4, so 13 minus 8 is 5. 6 minus 2 is 4. You spent $457 on goodies, candy. That's a lot of candy. I mean, to me, the word goodie means candy. Maybe it means something else too, but Mark works in a restaurant, earns $680 each week. His sister Lonnie is a manager at an electronics store and earns that much each week. How much less is Mark's weekly income than Lonnie's? How much less means to subtract. We take Lonnie's income and Mark's income and we subtract. 0 minus 0 is 0. Can't take 8 from 6, so 8 from 16 is 8. 12 minus 6 is 6. Looks like Lonnie makes exactly double what Mark makes. Okay. Perimeter is the distance around an object. It's how far you'd have to walk if you walked around. Later, we're going to talk about area. Area is how big the inside of a shape is. It's a way of measuring that. We'll talk about area later, but perimeter is to walk around the shape, how far it is around. Okay? So, Mary needs to put a fence around her garden to keep out rabbits. The garden is a rectangle that measures 12 feet by 10 feet. The long side is 12, the short side is 10. If we walk around, we're going to go 12 plus 10 is 22. And then we're going to walk around another 12 and another 10, which is another 22. And that gives us 44 feet around the entire garden. The perimeter is whatever I said it was. Was it 44? Yeah, 44 feet. Find the perimeter of each closed figure. So we're going to add up all the distances going around. Okay, well, I have 13 plus 2 plus 8 plus 8 plus 2 plus 13 plus 5. This here and this here are the same. So 8 plus 2 is 10, 10 plus 13 is 26. This will also be 26 because it's the same numbers. And then we have to add a 5. 26 plus 26 is 52. 52 plus 5 is 57 feet. It says the answer is 51, but it is wrong. Huh. 2 plus 8 is 10. 10 plus... Oh, 23. Sorry. I am wrong. 23 plus 23 plus 5 gives us 47. 6 plus 5, which is 51 feet, which is correct. Okay. Yeah. No, it's right. It did it right. I did it wrong. Let's look over here. So let's do another one. We have 2 plus 5 plus 33 plus 5 plus 35 plus 10. So we could add these together. This is 10. 10 plus 10 is 20. 2 plus 33 is 35. 35 plus 20. 35 and 35 is 70. 70 plus 20 is 90 feet. This is 90 feet. However, notice that all of these corners are 90-degree corners. What's nice is you can actually just kind of flip these corners out and make rectangles. This is a 35-foot rectangle by 10. Let's see, because I can take this chunk here and flip it out to make it a rectangle. And then it's 35 feet and 10 feet. So 35 plus 35 is 70. 10 plus 10 is 20. 70 plus 20 is still 90. That only works for things that are things you can make into rectangles. Okay. Triangle here. We're going to do 9 plus 7 plus 12. And you can do that on your own. Find the perimeter of each rectangle. So it's 9, and this side is also 9, 16, and this side is also 16. We can do this in lots of ways. 9 plus 16 is 25. There's another 25 here. 25 plus 25 is 50, and we're told centimeters, so 50 centimeters. Here we have 13 plus 14, that's 27 inches. That means the other two sides also add up to 27 inches. We can add those together to get 54 inches. That is an irregular shaped patio. I don't know why they chose that shape, although it does, I guess, have some symmetry. Like this half is a mirror image of this half, but it still looks weird. We want to find how much fencing is needed. Fences are perimeters because they go around the edge of the shape. So let's figure it out. We have 3. 1, 2, 3, 4, 5, 6, 7. Since they're all the same length and there are 7 of them, it's going to be 7 times 3 because it's 3 plus 3 plus 3 plus 3 plus 3 plus 3 plus 3. There are 7 threes we're adding together. Multiplication is repeated addition. I know we haven't done multiplication yet, but 3 times 7 is 21 yards. If we wanted to, we could add 7 threes together. 4, 5, 6, 7. 3, 6, 9, 12, 15, 18, 21. Okay. Write and solve your own story problem below that would involve the requirement to find the perimeter of a rectangle. Be ready to share your problem with the class. This here is something you have to do completely on your own. Just write some sort of word problem that has perimeter of a rectangle as part of it. So we have this problem here. We're told to, it says Olivia's backyard patio has a swimming pool. So here's the swimming pool. She would like to enclose the patio with a safety fence. Fences go around perimeters. This is a perimeter question. Below is a diagram of the pool and the patio area. She'd like to fence. How much fencing does she need? She needs fencing that goes around like this. but we don't know how big that side is. But here's the thing. We can put the fence down here, but it's the same length if we put the fence up here. We can put the fence over here, but it's the same length as if we put the fence over here. Which means that really, we need, this side is 30 feet of fence, and that means the bottom is also going to be 30 feet of fence. Because now we have a rectangle. See, we're just pushing this corner out to make a rectangle. This side is 25 plus 15, which is 40 feet, but this side of the rectangle is the same as this side of the rectangle, so this is also 40 feet. And then we have 30 plus 40 and 30 plus 40. That's 70 plus 70 is 140 feet. And yes, we did change the shape of the patio to do that, but we didn't change the length of the fencing. We can now use that 140 feet of fencing to do it on the edges that Olivia actually wanted, which were here. That's the same amount of fencing. So, again, we want to figure out the perimeter of the given figure. We notice that whatever this length is plus whatever this length is has to add up to this length. Whatever this length is plus, whatever this length is plus whatever this length is has to add up to this length. So really, it's 170 plus 170 broken into these two pieces, and 160 plus 160 divided into these two pieces. So we have 170 plus 160 is 330. That's to go from here to here. And then we need another 330 to go the other side, which is the same as what they did here. They figured out what this side length is and what this side length is using this process, and then they added all the sides together, but we don't need to know this side, and we don't need to know this side. We were just told to find the perimeter. That's it. So if we don't need to figure out this length and this length, why bother? So this here, this side is 23, which means this plus this equals 23. There are two 23s. That gives me 46. Hey, don't chew that cord. No, you don't chew power cords. My cat likes to come chew laptop cords. This 56 meters is the same as this plus this. So there's plus another 56, and then plus another 56. We get 18. 1 plus 4 is 5. 5 plus 5 is 10. 10 plus 5 is 15. This is 158 meters. This side and this side are the same length as this side and this side, which means we get 60 and 60 and 230 and 230. We can add those together. Six, 12, 18, 1, 3, 5. Given the perimeter of a closed figure, find a missing side length. So, for instance, if I know the perimeter is 32, but the perimeter is this side plus this side plus this side, I know that 32 minus this side and this side will equal the missing side. So I subtract off the 12, I subtract off the 15. I know this side has to be 5 yards because that is what adds to the others to give us the 32 yards of perimeter. The perimeter of the rectangle is 36 meters. I know this side is 8. Rectangles, the opposite sides are equal, so this side is also 8. So I know 8 plus something else has to equal 36. I also know that going on this side and this side is half the perimeter, so I could divide this 36 in half and then subtract 8. Whichever way we do it, it'll be the same. But if the whole perimeter is 36, then just going around one short side and one long side is half that. 2 goes into 3 one time. 1 times 2 is 2. 3 minus 2 is 1. Bring down the 6. 2 goes into 16 8 times. 8 times 2 is 16. 16 minus 16 is 0. There's no remainder. So this side plus this side equals 18. If I subtract 8 from both sides, I get the missing side is 10. That was somewhat of a leap in complication from what we've been doing, but we can check this by adding the sides together. If this side is 10, this side is also 10 because opposite sides of rectangles are the same length. So if I take 10 plus 8 plus 8, 8 plus 8 is 16, 1 plus 1 is 2, 2 plus 1 is 3, I get the 36 meters of perimeter. The perimeter of a rectangle is 56 feet. The width of the rectangle is 15, which means that these two sides are both 15. And these sides we don't know yet. 56 minus 15 gives me 6 minus 5 is 1. 5 minus 1 is 4. I subtract off the other side of 15. So I subtracted off that one. I'll subtract off this one now. I can't take 5 from 1, so I go 11 minus 5 is 6. 3 minus 1 is 2. Now I know that this 26 is split equally between this length and this length. Half of 26. 2 goes into 2 one time. 1 times 2 is 2. 2 minus 2 is 0. Bring down a 6. 2 goes into 6 3 times. 3 times 2 is 6. 6 minus 6 is 0. There's no remainder. That means that the missing sides are 13 feet. This side is 13 feet. And this side is 13 feet as well. Okay. We are chugging along. Module 1.5, multiplying whole numbers. Really, we probably should have talked about multiplying and dividing before these two problems. Did it say to solve these? Yeah, it said to solve these. I don't know that there's an easy way to solve these without multiplication and division. Anyway, multiplication is repeated addition. This just means 6 plus 6, or 2 plus 2 plus 2 plus 2 plus 2 plus 2. It's really cool how multiplication works this way. It's either there are two sixes added together, so there's 1 6 and 2 6s, or it's that there are 6 2's being added together. 1, 2, 3, 4, 5, 6. And whichever way you do it comes out the same. It's actually really cool that it works that way. So the picture makes it less mystical. So if I have 2 times 6, 1, 2, 3, 4, 5, 6, and 2, 1, 2. Notice that this rectangle I've drawn has 12 squares in it. And it doesn't matter if I look at it as 2 is how far left and right I am, and 6 is how far up and down I am, or if I draw it this way, This is still 2 by 6. It still has 12 squares in it. Either way I look at it, I either have 6 groups of 2 or I have 2 groups of 6. But at any rate, I still have 12 squares total. So whether I have 6 rows and 2 columns, six is my height and 2 is my width, or 2 is my height and 6 is my width. When I arrange these rectangles, I have the same number of squares in them. That is, I have 12 squares in each of them. Because it doesn't matter if I think of it as 6 groups of 2 added together or 2 groups of 6 added together, it still ends up being 12 as the total. Multiplication is repeated addition. A factor, the factors are the numbers you are multiplying together. And the product is the answer to a multiplication question. Okay. These are all ways to write multiplication. Um, I often use the asterisk when I'm writing multiplication on the whiteboard, so be prepared to see that in class. But we can use this stylized X, or we can use parentheses, or we can use a dot, or we can use an asterisk. So what we're doing here is we are rewriting the repeated addition as a single multiplication. Then we are going to simplify and we'll practice writing it 3 different ways. So this is 1, 2, 3, 4, 5, 6, 7, 8. 8 times 10, or this is the same as 10 times 8, or this is the same as 10 times 8, or this is the same as 10 times 8, or 8 times 10, 10, whichever way you want to do it. We also want to simplify and get an answer, I think. Yeah, 8 times 10 is 80. 1, 2, 3, 4, 5, 6, 7, 8. 8 times 8, 8 times 8, 8 times 8, and it's 64. We're going to go through a lot of ways to visualize multiplication now. If you have trouble with your multiplication tables, there are practice problems you can find on the Canvas page for the course. So, and again, I'll show you some if the lecture notes don't have the ways that I like to visualize this, I'll show you those in addition. But let's just go through the lecture notes right now. And yeah, this is exactly what I was saying, is that we have commutivity here. Remember when we did commutivity with addition where like 3 plus 4 equals 4 plus 3? Same thing. 3 times 4 equals 4 times 3. We can think of it as we're doing 6 jumps of 3. 1, 2, 3, 4, 5, 6. Or 3 jumps of 6. The same thing. Okay. Rewrite each expression in expanded form, draw a number line to model the expression. So here we have, this is 3 plus 3 plus 3, which is 9. And we can draw a number line, and we go from 0, we go to 3, to 6, and to 9. Okay. we have here 6 plus 6 plus 6 plus 6 plus 6. We can go, this is 30, by the way. We can also think of it as as doing 5 plus 5 six times. So we can go 5, 10, 15, 20, 25, 30. This is 1, 2, 3, 4, 5, 6 jumps. A classroom has 7 rows. There are 5 desks in each row. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5 on each row. Draw a model to represent how to find the total number of desks in the classroom. Drawing models is a good way to understand problems. We can tap into parts of our brain that might not be activated from just reading the words if we draw a picture. So I drew 7 rows with 5 desks in each one. How many ways can you write a multiplication equation to represent the situation? Well, 5 times 7, 7 times 5, and then all of the different symbols that we could use. All of that, yeah. Lots of ways. Be ready to discuss in class. Okay. Find an equation from the list that can represent each situation. So let's see. We have, this is 5 times 3 equals 15. This one is 2 times 11 equals 22. 6 hands were on a table. Each hand has 5 fingers. 6 times 5 equals 30. This is 5 groups of 10. This is 4 rows of 4. And this is 8 times 2 equals 16. Wasn't too bad. Write your own scenario or situation and the multiplication equation that would match this model. We have 2 times 1, 2, 3, 4, 5, 6, 7, 8, 9. 2 times 9 is 18. It says write a scenario, so write a word problem for that as well. So you can come up with whatever word problem you want to go with that. We've already talked about the commutative property of addition. They're just saying you can switch the order and get the same values. So we're going to use the commutative property. Notice that division is not commutative. So when we see two things multiplied together, we can switch the order. You see these are multiplied, so we can switch the order. We can switch the order because these are also being multiplied. And we cannot switch the order for division. Okay. Identify and apply the associative property of multiplication. Associative is exactly like it is for addition. We can switch which multiplication we do first. So, like with this one, 10 times 3 is 30. 30 times 5 is 150. But I can also go the other way. 3 times 5 is 15. 3 times 5 is 15. 15 times 10 is also 150. Oh, I guess they have it written over here. 7 times 3 times 5. 3 times 5 is 15. 7 times 15 is 105. 7 times 3 is 21. 21 times 5 is 105. Notice that this is the same as this. And this is the same whether we did the 10 and 3 first, or whether we did the 3 and the 5 first. This is the same as this. So, notice division is not associative, so we can take this one and we can rewrite it as 7 times 5 first times 9. That's fine. This one, division is not associative. Doesn't apply. The identity property is 1 is an identity for multiplication. In fact, 1 is the only identity for multiplication. Multiplying by 1 does not change the value. 3 times 1 is 3, 1 times 30 is 30. Whatever number you're dealing with times 1 is itself. So, the numbers that fill in the blanks. For this one, it's 24. 1 times 24 is 24. For this one, something times 43 is 43. The only thing that you can multiply 43 by to get 43 is 1. So you're going to have to solve those on your own. That's how you do that. Multiplicative property of 0. 0 times any number is 0. Number times 0 is 0. 0 times a number is 0. We get here 31 times 0 is 0. Something times 76 is 0. Well, 0 times 76 is 0. You fill in these blanks on your own. We're going to identify these rules. So this is the multiplicative property of 0. This one is, well, it's one of these. And if you don't know, go look at all of these boxes that define them. You can do this one on your own. Here's a multiplication chart. You should memorize this chart. Memorize is maybe a strong word. You should know this chart. Every row and column is its own pattern. This row you're adding 5s. This column you're adding 9s. So like 0 plus 4 is 4, plus 4 is 8, plus 4 is 12, plus 4 is 16. You're just adding 4 on this row. But you should get this chart down, because when I want to multiply 8 by 12, it's nice to know that it's 96. So you should know these. And there are assignments on Canvas that you can do. They are not for points, but they are available for you to use to practice. So go practice if you are not very good with your multiplication tables. 6 times 4 is 40. Sorry, 6 times 7 is 42. 3 times 9 is 27. You can do the other ones yourself. Write at least 2 different ways you can multiply each expression. So this can be 35 times 2, which is 70. Or it can also be 7 times 10, which is still 70. Okay? You can do this one on your own. The distributive property is how multiplication and addition behave nicely with each other. Also subtraction. So if I am multiplying the answer to an addition problem by a number, I can either do the addition first, like the parentheses say to do, and then multiply whatever I get by the number, or I can multiply each of the two numbers first and then add after. So this here, I can either do this as adding first and getting 3 times 7, which is 21, or I can multiply first. 3 times 2 is 6, 3 times 5 is 15, 6 plus 15 is still 21. It says rewrite expression using distributive property, fill in the missing factor, product, or addend for each accompanying area model that represents the distribution and simplify your answer. So this is 3 times 2 plus 5, so this is 3 times 2 plus 5. This one here, I can do it as 2 times 12, which is 24, or I can also do it as 8 plus 16, which is 24. So 2 times 4 gives me 8. 8 times 2 gives me 16. That adds up to 24 either way. This adds up to 21. 10 minus 2 is in here. 7 goes there. 9 minus 5, so I have 9 times 4 is 36. 4 times negative 5 is negative 20. Rewrite each expression using the distributive property. We can either do this as 30 plus 55, which is 85, or we can do this as 5 times 17, which is still 85. 90 minus 18, which is 72, or 9 times 8, which is 72. You can do the other ones on your own. Okay. Multiplying numbers by multiples of 10. So, because we use a base 10 number system, remember we talked about in class how each of our numbers is broken up into positions that represent groups of 10. This is the ones place, this is the tens place. Because we have a base 10 base 10 number system, multiplying by 10 is really easy. We just put zeros at the end of the number when we multiply by 10. This works also for multiplying multiples of 10. So if I want to multiply 70 and 200, this is the same as multiplying 7 and 2. And since this is in the tens place, I have a 10 here. And since this is in the hundreds place, I have 100 here. 70 times 200 is the same as 7 times 2 times 10 times 100. And multiplying by a power of 10, like 10 or 100, is just placing the zeros at the end of the number. 7 times 2 is 14. I have 1, 2, 3 zeros to put at the end. This equals this, like it says there. So with this, I have 3 zeros in my power of 10. Powers of 10 are always the number 1 followed by some number of zeros. When I multiply by a power of 10, I just take those zeros and stick them on the other factor. So 176, and then put 3 zeros at the end. I have here 2 plus 4 is 6 zeros, so I'm going to put 6 zeros at the end. 3 times 6 is 18. I put 6 zeros at the end. This is my answer. I'll let you do this one on your own. You can check these with the calculator, but do them by hand first. So we're using the distributive property to make multiplication easier. Notice 6 times 99. 99 is just 100 minus 1. And it's easy to multiply 6 and 100, and it's easy to multiply 6 and 1. So it's easier to do this 6 times 99 as a distributive question, a distributive property question, because I can just multiply 6 by 100 and 6 by 1 and subtract them, than it is to think of 6 times 9 is 54, carry the 5. 6 times 9 is 54. 54 plus 5 is 59. Like, it's the same answer, but it's easier to look at. This problem, by the way, can be represented with this picture. We have 6 times 99 is what we're looking for. 6 times 100 is 600. 6 times 1 is 6. If I take this 600 and subtract off that 6, I'm left with 594, which is the answer that I'm looking for. Here I have 371. Here's 300 plus 70 plus 1. 5 times 300 is 1500. 5 times 70 is 35 with a 0 at the end. Just the 1 0 because we have just 1 0 there. 5 times 1 is 5. If I add these together, I get 1855, which is the multiplication problem that I'm trying to do. The reason this works this way is because the area of a rectangle is the length times the width. So this here is the length, and this here is the width. Writing it out as a rectangle is a visual way of doing multiplication because the area of a rectangle is multiplication. We want to use the distributive property to make these problems easier. So this is 3 times 30 plus 3 times 5. 3 times 30 is 90. 3 times 5 is 15. This adds up to 105. This one here, this is pretty close to 600. It might be easier to do this problem as 6 times 600 minus 1. 6 times 6 is 36. 6 times 600 is 3600. 6 times 1 is 6. I subtract. 3594 is my answer. This one here, if I want to multiply this out, this is 4 times 600 plus 4 times 90 plus 4 times 8. 4 times 600, 4 times 6 is 24, so 4 times 600 is 2400. 4 times 9 is 36, so 4 times 90 is 360. 4 times 8 is 32. I add these together, I get 2, 7, 9, 2. Or I could also do it this way. This is pretty close to 700. This is 4 times 700 minus 2. 4 times 7 is 28, so 4 times 700 is 2800. 4 times 2 is 8, so I'm going to take 8 off of this. This gives me my 2792. Either way, it gets us the same answer. Estimating products using front-end rounding. So, if I round this to the front, I get I look at the check digit. This is a 2. It rounds down. So this is the same as 4 times 8,000. 4 times 8 is 32. So 4 times 8,000 is 32,000. This is my estimate. With this one, you usually only need to front end round one of the numbers, but you can front end round both numbers. If I just front end round this number, this is going to be about 20 times 75. 2 times 75 is 150, so 20 times 75 is 1,500. That's a pretty good estimate. If I front end round both of these, I get 20 times 80. 2 times 8 is 16. I put 2 zeros at the end. So, they're close. They're not equal because they're also not exact values. Like, these are just estimates of whatever this product is. Let's front end round this. And let's front end round both numbers. So I'm going to round to here and here. So my checks are there and there. This rounds to 6,000. This rounds to 200,000. So I have, this is approximately equal to that. This is 6 times 2 is 12. That's my undo button there. There. Oh, look there. Hmm. Okay, so 6 times 2 is 12. And then I have 3 plus 5, that's 8 zeros. And there's my approximation. It's about 1.2 billion. A big number. Multiply two whole numbers to find the product. Those are the steps for it. Let's do some of these as examples. So I want to multiply this. I can write this in either way, but usually it's easier to put the number with fewer digits on the bottom. So let's do it both ways and show that they give the same value. 4 times 2 is 8. 4 times 7 is 28. 2 times 4 is 8. I move to the next digit, so I put a 0 here to represent that I'm in the tens place. 4 times 7 is 28. I add these, I get 288. Same thing. Over here, I'm not going to do this one both ways. I will do this one both ways. So I have 18 times 75, and I have 75 times 18. Usually, if you have a choice, if they have the same number of digits, you might want to pick the one that has smaller numbers in it, like ones and zeros. Ones and zeros multiply really nicely. Or you might want to pick the one that has repeated digits if you have that. The multiplication goes like this. 5 times 8 is 40. Carry a 4. 5 times 1 is 5, plus 4 is 90. Next digit. 7 times 8 is 56. Carry a 5. 7 times 1 is 7, plus 5 is 12. And I go 0, 5, carry a 1, 13, like that. With this one, 8 times 5 is 40. 8 times 7 is 56, plus 4 is 60. 0, because I'm in the next digit now. 1 times 75 is itself. I add 0, 5, 13. Now this one seemed like an easier way to do it because this one, multiplying by 1 is really nice. So if you have a choice between two numbers that are the same size, you probably want to pick the ones that has ones, the number that has ones and zeros in it. This is a neat way of multiplying. My sixth grade math teacher called this Egyptian multiplication. I don't know why, because the Egyptians did not have Arabic numerals like this. But maybe they wrote their multiplication problems with these diagonals. Don't know. But it's kind of neat. Maybe I'll do one of these problems that way for you. Maybe I'll do this one that way. So the way that we do this is we're going to write our digits down the side of the right side of the square, the rectangle, 294 and 86. This is exactly the same procedure as our normal multiplication, but it takes up a little bit more space, and because of that, it seems less crowded, and that sometimes is something the students like. I'll just draw this a little straighter here. So, as I said in class yesterday, there's always this balance between if you write more things, you have more explanation, but it also takes more space and might look more intimidating to try and figure out how to read it. Writing fewer steps is going to look simpler, but it's also going to require you to know more to decode what's being written. Anyway, we have this written out like this. I'm going to do 4 times 6 is 24. One of the nice things about this is that I don't really have to start on any particular place. I can just look at the multiplications that are easy for me. Maybe 6 times 2 is 12. I'm putting the tens on the upper part of each square and the ones place on the lower part of each square. Maybe like I forget what 6 times 9 is, and I think, well, I'll just come back to that later. 8 times 2 is 16. 8 times 9 is 72. And 8 times 4 is 32. And then I come back to like, okay, do I remember it now? If I don't, maybe I just write down 6 9s and add them together. Eventually, I come up with that it's 54. Then, so with our traditional vertical multiplication, there's really not a, oh, I'm stuck on this multiplication step. Let me just skip and come back to it. It's hard to do that here. One of the nice things about this is because of how it's written, you don't have to do it in a specific order. You can decide something's hard and come back to it later. Once I do this, I add up all the diagonals. So this is just a 4. There's nothing in its diagonal. I have a 4 plus a 2 plus a 2. That's an 8. And a 2 plus a 5 is a 7. 7 plus 3 is 10. 10 plus 2 is 12. So I take a 2 there, and I write a 1 up here for my 12. 1 plus 1 is 2. 2 plus 6 is 8. 8 plus 7 is 15. I write a 5 there. Carry a 1. 1 plus 1 is 2. So my answer now is 2. I read it this way. 5, 2, 8, 4. And if I did it the conventional way, I'm going to write this a little higher, actually. I might need some vertical space for this. I write 294 times 86, and I do it the conventional way. 6 times 4 is 24. I carry a 2. 6 times 9 is 54, plus 2 is 56. 6 times 2 is 12. 12 plus 5 is 17. Next digit, 8 times 4 is 32. Carry a 3. 8 times 9 is 72, plus 3 is 75. Carry a 7. 8 times 2 is 16. 16 plus 7 is 23. I add these together. I get 4, 8, 2, carry a 1, 5, and 2. And notice that these numbers are in fact the same. This is a little more compact than this, but there are some pros to this, like being able to do steps out of order. There's really no like swapping the order of these things here. And again, because it takes a little more space, it looks a little bit less dense and compact, and it might be less scary to look at because of that. Maybe. It's up to you. Okay. We can practice more multiplication in class. So, I think what I'm going to do is upload the recording right now, and class is 2.5 hours long. If I stop now, we'll just count 40 hours of you doing work, not 40 hours, 40 minutes of you doing classwork and maybe needing to pause, rewind, and rewatch. We'll count this as our lecture for Tuesday. So, hope you're having a good weekend. I will upload this now, and we will try to meet together on Wednesday and go over any questions that you have. So, looking forward to talking about exponents and square roots on Wednesday. Have a great weekend. Bye.